Okay, so now let's have first a brief review of this time-independent Schrodinger equation. Okay, so we have learned last time. Okay, we know that the time-dependent Schrodinger equation is just like this one. And this potential in general could be time dependent. Okay. The wave function, of course, could also be time dependent. So this is a general case. Right? For example, you can have a potential Vxt that equals to the usual potential for the harmonic oscillator. Right? We know that this is the potential for the harmonic oscillator. Okay. And now we apply a force F, but this force is time dependent. It's say omega 0 times t. It's an oscillating force. You know that this is a driving harmonic oscillator. We call this a forced harmonic oscillator, right? And then times x. Okay, so that is the case that you have for a potential that is time independent, time dependent. Okay, so that means in general, Vxt can depend on time. Okay. Okay. But we consider the case that, let us just consider a relatively simple case. Okay, Vx, okay, independent of time. Okay, and then in this case, we can do the separation variable is x and t. Okay, it's possible, right? So we can write down this xt just equals to, for example, phi x times ft. Okay, and then we just follow the standard procedure of this separation variable method. We write down the equation. The solution is that then the solution is going to be per psi xt actually is going to equals to per psi e x e to minus I e t over h bar. Okay, the time dependent part is very easy to solve, and then the time independent part becomes something like this one. Now you have only differential over the with respect to the coordinates. Okay. Right. So this is the time independent Schrodinger equation. Okay. Okay. Of course, you can also write down this one as right, quite a shorthand notation. Okay. Right. So this way you have a more concise notation. Okay. Right. And this h is an operator. Okay. You can also write it as the momentum operator over 2m plus v as function of this position operator. Okay. And you know that this operator per psi x actually is defined as h bar of I, and do the differential with respect to x once. Okay. And this x operator is just very simple, just equal to x times per psi x. Okay. Right. So this one is called a Hamiltonian. Right, because it's just the kinetic energy plus the potential energy. Okay, so it just has the meaning of energy. So then this E is called a eigenvalue of H, also called eigenenergy. Okay, and this psi E is called a eigenfunction of H. Okay. All right, so that's just some terminology. Okay. Right. So then the problem. So the solution reduced to. So the problem is to find E and psi E for H. Okay. All right. So this is the general problem in quantum mechanics. Once you have Hamiltonian, you try to find the eigenfunctions and the eigenvalues for this Hamiltonian. And later, we actually will spend quite some time in this course to use more and more examples. Okay. So in general, you can have more than one solutions. Okay. So you can have, say, for example, you can have many solutions. Okay. Psi m x. Okay. So that means you can have H psi mx that equals to em psi mx. Okay. N equals to 1, 2, 3, and so on and so forth. So you can have many of them. And for each of this one, you have the solution of this xt, right? That will equals to, of course, according to what we have derived earlier. We'll give this one, right? And you know that this time-dependent Schrödinger equation is linear. It's a linear PDE, okay? Right. So that means if you have, say, for example, Hamiltonian psi 1 xt equals to I h bar partial t psi 1 xt. And you have this one equals to I h bar partial t psi 2 xt. You have two solutions. Suppose you have two solutions. And then since this one is a linear partial differential equation, so that means you must have the linear combination of these two, C1 times psi 1 plus C2 times psi 2. Should also be a solution, right? That's very easy to check. You can just do the expansion, right? Do the linear expansion, you can go to this one immediately, okay? So if you have this one, and then you got this one, right? So that's a property of this, the linear one, okay? So this indicated that the general solution, so once you have, suppose you have already found the eigenstates, okay, psi m. So then the general solution can be always written as the summation of m coefficients. And then you have these eigenstates or eigenfunctions already obtained. And then each of these one evolve like this. Okay. So you do the linear combination for this one. So this one is a solution of this one, right? So finding the eigenenergies and eigenfunctions This is EM, sorry. And the percent M leads to the solution of the Schrodinger equation, right? Okay. So that means as long as you found all the eigenvalues and the eigenfunctions, you actually solve the problem. Okay. So this is what we have, last time. Okay. And we also mentioned a little bit about this free particles. Okay. Suppose we have a free particle. That means Vx is equal to 0. Okay. And then Hamiltonian is very simple. It's just minus partial squared over 2m d over dx squared. Okay. And then you know that, and then this one, you got all of this one, right? So this can be solved easily. So the solution are just the eigenfunctions. Is the plane waves. Okay, that's the percent kx equals to EIKX. Okay, so you can easily check this one. Let's do the check. Okay, partial squared 2m d over dx action percent k, right? So you can check this one. That equals to simply minus h bar squared over 2m, and d over dx. You're acting this one once on this one, and this differential on the exponential function of course gives you ik, the factor, right? So that gives one factor ik. Okay, and then you do this one again. Okay, and this gives you another ik, so that gives you minus h bar squared over 2m ik squared EIKX, right? So the result is simply h bar squared over 2m k squared EIKX. So immediately you know that this one is just eigenenergy. Right. So you immediately obtain that this EK just equals to h bar squared k squared over 2m. Okay. And you know that k can be any value. So k any value between minus infinity to plus infinity. And the energy, of course, because there's a k squared, is always positive. And why not negative energy? Okay, so there's a few points to be discussed, right? So the question is why E is not a lot. Okay, in that case, you can say that, and then you have K is going to be equals to I plus or minus I square root of E, right? Times 2m over h bar. Okay. So it's an imaginary number, and then you have this EIKX that will equals to e to plus or minus x times 2m. So that's the absolute value, sorry. Absolute value of E over h bar. And this one will goes to infinity at x goes to plus or minus infinity, right? So that means you cannot form a normalized wave packet. Okay. So this one is E less than 0 is unphysical. Okay. So you can see that the physical conditions in this case, what's the physical condition? That's the probability x dt should equals to 1, right? So this is a physical condition. And this one actually leads to the mathematical condition. The mathematical boundary condition. What is this one? So there's a percent x, should not goes to infinity at x equals to plus or minus infinity, okay? And so otherwise you cannot form a wave packet that is normalizable, okay? All right, so this is one thing that we considered last time, okay? Right. And of course, let's check a little bit physical meaning of this one. So you know that you have a state, this is eigen. You know this is plane wave, right? So you know that according to De Broglie, h bar k should be the momentum, right? Okay, and this ek equals to h bar squared k squared, of course, is the energy. Okay, or ek omega k equals to ek over h bar, that equals to h bar k squared over 2m, is the angular frequency. Okay, of this state. Now to have more meaning of this one, let's check the current density. Right, remember the current density G is defined as 1 over 2m. Okay. And per se complex conjugate. And this one, the momentum operator acting on this per se minus the momentum operator acting on per se complex conjugate, plus, and the per se, right? So let's calculate this one. And the momentum operator, we know that is just h bar over I, d over dx, right? Let's do some check, okay? Now we consider this to be the eigenstates of the plane wave, okay? This one. And we put this back on this one, so you can say that the P acting on EIKX, that will equal to what? That will be equal to I over h bar, d over dx, EIKX, right? And differential of this expansion function gives you IK times this expansion function. So the result will be h bar k times I divided by I, EIKX. So that's nothing but just h bar k, EIKX, okay? So you got also another interesting equation right here, okay? So we're going to discuss this one a little bit later, but not at this moment. But if you are curious, so this one actually can be written as P per sec k equals to h bar k per sec k, right? Okay. So this is the momentum operator acting on this wave function, give you a constant times this wave function, okay? But anyway, we will come back to this point later, okay? So you put this back into this one. So the result is J just equals to 1 over 2m, okay? EIKX complex conjugate, so that's minus, okay? Times h bar k times EIKX, right? And then plus another term, that's the complex conjugate of this one, basically, right? So this one is nothing but just h bar k over m. So this current density, now it's just the velocity, right, of this particle. Okay, so you can see that there is indeed a physical meaning of this K and EK and this current density. Right. So that's the case for this the free particle. Now we can consider more general cases. That's Vx is not 0. Right. So there are many different cases. Okay. Let's give a few examples. One famous example, and we're going to study very thoroughly, is this harmonical oscillator. Right. So in this case, you know that this one equals to kx squared, right? Over 2. K is just the spring coefficients for this harmonic oscillator. And this one can be also written in terms of the frequency of this, angular frequency of this oscillator is m omega squared, okay, times x squared, right? So if we plot this one, it's a parabolic curve, okay? So this is x, so this is Vx, right? So that's one of this potential, okay? You can also have a 2D harmonic oscillator. For example, you can have, say, Vxy that equals to m omega x squared over 2. So you have harmonic oscillator in the x direction, but you can also have this in the y direction. Okay? Or you can have this one in 3D, okay? All right, so this is, for example, one of the cases like in the cold atom trap. So you can trap cold atoms use this so-called harmonical potential. Okay, so you can have m omega. Let's say you have a transverse frequency x squared over 2, and then you have this y squared. So in this case, you have a potential that's confined in the x-y direction with this frequency omega transverse. But you can also have the frequency in the z direction is different. Okay, right. So this is the case that you can have the potential is symmetric in the x-y direction, but in the z direction is slightly different. Okay, right. So this is 1D, 2D, 3D. Okay. Right. So this is just one of the examples. You can also consider another example. Say, let's consider a hydrogen atom, for example. And the hydrogen atom, let's fix the position of proton because it's heavy. Okay. So if it's heavy, let's say just it's not moving at all. Okay. And then just we need to consider this potential filled by the electron from the charge interaction. So we know that this V x, y, z actually is symmetrical in different angles. So it's their charge. The charge is E. One is positive, another is negative. So it's E squared. Okay. And then this one should be negative, right? And the constant is 4 pi epsilon 0, and then this one is just R. Okay. So if we plot this one, it something goes like this one, right? So let me use slightly different colors. Okay. Okay, so this is V, for example, R. Okay, right. So this is another case. So there are different examples, right? We are also going to consider a lot of one-dimensional cases. For example, you can have this so-called quantum well. The weight of this one is W, and this potential V goes to infinite, for x greater than W or x less than 0. Okay, so this one is V greater to infinite. at this region, V just equal to 0. So this is another case that we're going to study. So that's called an infinite quantum well. Right? But you can also consider so-called finite quantum well, for example. Okay, so this is still with W, and this one is V equal to 0, and this V equals to V0. Right, so that's another case, right? You can also have something like this one. Okay. Well, you can have more complex cases. So you can have something like this one. Okay. So it's up to you to have different kind of quantum wells. And many choices, right? So we will study some of them to get some ideas of what will be the states within this kind of potentials, okay? But anyway, if we have this one, so we have Hamiltonian just equals to P squared over 2m, and plus the potential that a problem specifies, okay? And we have solutions of this one called eigen functions and eigenenergies. And we know that the time dependence of this one is going to percent mx e to minus I e m t over h bar, right? And the general solution is just simple as, okay, cm percent mx e to minus I e m t over h bar, okay? So the problem is just to solve those differential equations. So this is the core problem, okay? Once you solve this one, then you solve the problem actually. Okay, so we will spend some of the time to solve this one. Sometimes it's easy, sometimes it's difficult. Sometimes we have to resort to numerical calculations, or sometimes we have to use some physical insights and approximations. Okay, there's no systematic way, there's no exact solution, analytical solution for all the problems, okay? Make sure. This is why the physical careers is still existing, okay? Because nobody knows how to solve this problem in general. So that people have to resort to experiments, numerical calculations, approximations of physical insights, experience, so on and so forth, so that you can still survive in this real world, okay? Otherwise, the life is boring and the physical career is disappearing. Okay. All right. But there are a few properties we can mention this one. Okay. So if we consider this is so-called bound states. Okay. So bound states, that means this percent mx goes to 0 properly. That means fast enough. What means fast enough? So this is, physically, I mean, if you have a potential, for example, if you have a potential like this one, I can have a state. This is the energy, EM, okay? And you can have a state that goes like this, by the join. So you can have a state that goes to 0, and then inside this one, that's still by join. This is better. Okay, so this is the wave function. You can have wave function like this one, but this one goes to 0 fast enough so that this integration, so that's the explanation of this fast enough, converge to a constant. Okay, so that means we can normalize this one. Okay, so this basically means the bound states can be normalized. Okay, So that means we can write down this percent mx dx equals 0. Sorry, equals 1. So that's one thing that we know for this boundary states. Secondly, the boundary states are discrete. So that means if EM is an eigenvalue, eigenenergy, okay, and then there's no state close by, okay. So you have this. So basically, you have this discrete. This is E1, E2, E3, okay. So you have this one to be discrete. It's not like a continuum, okay, right? So if you consider the solution of the free particles, in that case, you see that the states are not boundary states because they cannot be normalized. Secondly, the energy actually distributed continuously from 0 to positive infinity. But for boundary state, this must be discrete. So we are not going to prove this one. So there's some theory in PDE to show this one is correct. But you can have some argument, right? You can say that suppose you have a solution like this one. If we change the energy small slightly, and then you will have to change this wave function also very small slightly. And then you know that once you have a solution, you put this back into this one, you make a small change on that one, you find that, the change actually will not be a solution, okay? The change must be large enough to have another solution, okay? So by that's some hand wave argument. You know, I'm not going to give you the mathematical proof at this problem, but you can check. So let's just add a small change of the wave function, see what will happen. Okay, a small change of wave function is not going to be a solution. Okay, right. So that's something that you can check, but that one is related to the variation method. So we're not going to touch at this point yet. Okay. All right. And there's another property. And this wave function actually, if you have two wave functions, you do the overlap integration of this one, of one of this one, and this one actually will be 0 if m is not m. That's called orthogonal. Okay. So that means these two wave functions are orthogonal. So if we summarize these two together, so this can be written in one condition. So we say that percent mx integrate together. This will equals to a delta function m and m. That means equals m equals if they are the same, this is 1. If they're different, this is 0. Okay, so that means so this basically means 2 plus 3 means that all these states are called also normal. Okay, they are orthogonal. They are normalized. So they put these two together, they are also normal. Okay, but it's just a name. And there's another property that I'm not going to prove. Okay. And all of this one are complete. What does this mean? That means any function percent x, okay, if this is important, okay, let me use the red color. If the same boundary conditions, okay, if it is of the same boundary conditions as this eigenstates, okay, only with this condition, okay, if it's not this condition, you cannot do this, okay, so can be expanded as Okay. And the Cm, this coefficients, is called a expansion coefficients. Okay. And this one actually, Cm is unique. And that means you cannot have two expansions that have, have different coefficients for the same wave functions. So let me prove this one and show you constructively how can we obtain these coefficients. Okay. Right. Remember, if we have an expansion like this one, okay, let's try to calculate this integration. And we put this back into this, so that way equals to percent mx summation of m cm percent mx dx, right? So this is a lot of fun of doing this kind of mathematics, of these eigenstates. And they can do a summation outside, of course. Now use also normal properties. So this will give you a delta function, right? So that means you got something like this one. So sorry, you do the summation of this for m. So if n equal to m, this is going to be 1. If m is different and this is 0, so that means this one simply just equals to Cm. So that means Cm is determined, okay? So this one proves, first of all, Cm is unique. And secondly, Cm can be found, right? So that if you have any function of this one, so you can find these coefficients, okay? To make the story complete, okay, and this is not required, it's optional. So if you consider both bound states and the continuous states, okay, so you can have also normal. This is a misspelling. So that means you can have states percent m. You can have states percent k. M is discrete, k is continuum. Okay. So k is continuum. M is discrete, for example. Okay. So you actually have delta m and m equals to percent m and dx, and 0 equals to percent mx and the percent k x dx. And then how about this one? Percent k complex conjugate, percent k prime x dx. So this one we actually use something very similar to this one. So if k and k prime is different, it's just 0. But if they are not, if they're the same, we use something called a delta function. That's infinite, okay? Because it cannot be normalized, so it's infinite, okay? So this is also normal condition. And the complete is that any function can be written as, something like this one. And then for the continuum, okay, for the continuum, this should be integration. Let me write down ck, okay, so that you use the same notation. Okay, dk. So you can see that this one actually is very similar to the Fourier transform, right? So you can compare this one to the Fourier transform. Okay. So this one is just the expansion of the discrete states. Okay. But this part, let me say, is optional. Okay. So you don't know this one, but to be complete, you can just have this one. Okay. Right. So this is for the bounded states. For this continuous states. Okay. So this is pretty much what we have today. Okay. Let's take a break. If you have questions, you can just type in the chatting room. Okay. And then after the break, we're going to have the discussion of the exercise. Okay. So to do this one with some examples and some techniques to get more familiar with this formalism. Okay. All right.